For the first half an hour, I think we will talk about the usual question session, and then for the last 1 hour, we'll have this career path kind of session. So basically, you can probably also think about now if you have any questions, if you are going to continue for your graduate study in master degree or doctorate degree or postdoc. Yeah, basically, if you have any questions about applications or to the Europe or to the States and so on, so you can ask during that time. Yeah. Okay, I think today we have a last lecture by Misha. You tell us, I think, about some dark matter and also inflation. Okay.
Mm-hmm. Yeah, thank you very much, Shan. So, yesterday we had a lot of baryogenesis in different incarnations, and I also started to discuss different constraints on dark matter particles. There is one constraint which I mentioned, which is a lower limit on the mass of dark matter particle, which is due to Tremaine and Gunn. I didn't explain it, so I will spend 2 minutes explaining it because it's two-line demonstration. Okay, so imagine that you have some volume with the size r, and you have fermionic particles there with momentum p smaller than p0. Okay, you can find out how many particles are in this box. You can put an upper limit on the number of these particles, and this upper limit will be n smaller than integral d3p over 2 pi cube times integral d3x. Okay, and then what you do, you put here the distribution function for fermions. And distribution function for fermion cannot exceed 1 because you can only put one fermion in one quantum state. And so n is smaller than this. And this is of the order of p cube r cube. Okay, p0 cube r cube. And I omit all factors like 2 pi because we are making an order of magnitude estimate. So this is a constraint on the number of particles, and so we can get a constraint on the mass of this object. So mass of this object will be smaller than mass of fermion. Instead of momentum, I'm going to write mass of fermion cube, velocity cube, and then we have r cube, where r is the size of the system. Okay, so this is stuff which comes just from Pauli exclusion principle. Well, at the same time, this system, the system of dark matter particles, should be in virial equilibrium, meaning that m mass of this dark matter particle, m times mass of this object times g Fermi divided by r. So this is potential energy of all this stuff. It should be of the order of kinetic energy, which is mf v squared over 2. Okay, so from this relation, of course, mass of fermion cancels out because gravity acts, well, because there is equivalence principle. And so from here, you can get an estimate, another estimate of the mass of the object. And so mass of the object should be of the order of v squared times r divided by g Fermi. Not Fermi. Sorry, this is not Fermi, this is Newton. Okay, and so now what we do, we unify this and that. Okay, so we have to write that this mass should be smaller than mass of fermion to the 4th power, velocity cube times r cube. So you see velocity square cancels, r goes to r squared, And so you get a constraint that fermion mass should be greater than what? Than 1 divided by velocity times r square to the power 1/4. And this is Ström-Gunn bound. So how do you apply the Ström-Gunn bound in cosmology? You take a particular dwarf galaxy, you estimate, and I forgot Gn. Okay, so now it's better. You get a size of this object, and then you measure the rotational velocities, you put the numbers, and you get this constraint. Okay, so it's very easy. Fuzzy dark matter I discussed. So I will discuss yet another constraint on dark matter particle, which is also very important and which distinguishes different types of dark matter, such as cold dark matter, warm dark matter, and hot dark matter. So what this constraint is about. So if you have dark matter particles, these dark matter particles must be very weakly interacting, otherwise we would see them if their mass is small enough. And these particles, they free stream. Okay, so suppose that these particles are decoupled, and then they simply propagate over the universe, and they don't collide with any other particles. The structure formation, so we have a universe which is almost homogeneous, but there are small fluctuations there, and then this fluctuation may start to collapse and form the structure only when the universe enters into matter-dominated epoch. So it happens that this type of collapse doesn't happen if we are in radiation-dominated epoch, well, mainly because there is pressure which prevents everything from collapse. Okay, and what you can compute. So imagine that you have this a little bit bumpy universe. Okay, so there is an excess of density, there is somewhat smaller density, and so you have this type of picture. Okay, and now here you have dark matter particles which will be floating out from this region because they do not collide with anything else. And if the distance which these particles travel is larger than the size of this inhomogeneity, it will smear all inhomogeneities, and you will get a situation which is uniform. Okay? So what does it mean? This means that in this case, the very small structures, the structures which are smaller than the free streaming scale of this dark matter particle, they cannot be formed. Why? Because the inhomogeneities went out from this region. Okay, and in this way, we can also get very important constraints on dark matter particles, and these are also constraints on their mass, but not only on their mass, but also on their properties, on their velocities at the time when the matter-dominated epoch starts. Okay, so, and this is how it works. I take a sphere of the size L, where L is the free streaming scale. So this is the distance our dark matter particle can go at this epoch. So this is nothing but the volume of this sphere, and rho is the density of matter, dark matter plus ordinary matter. How do we compute the free streamal scale? If the universe were not expanding, then the distance the particle would traverse would be just their velocity, right? And so then the differential equation, it will be very trivial. The distance over the time is equal to velocity. Now, the universe is expanding, and therefore there is yet another source for these particles to travel, and this is just the Hubble expansion. Okay, so this is the equation, differential equation, which tells you what the dark matter particle will traverse. This equation you can solve. Okay, this is an elementary differential equation, and this is the result. The result includes the scale factor, which is time dependent. If it were not time dependent, you will simply get v dt, which is a triviality. Okay, and now you insert everything into this equation. Okay, and this is what you are going to get. Written in some convenient units. So this free streaming mass is 10 to the 10 solar masses. So all fundamental constants are inserted in this equation. Then there is some convenient normalization scale. M is the mass of dark matter particle. 7 keV is just normalization. And then there is some factor which basically of the order of 1. In many cases, it could be much less than 1 in some other cases, which I'm going to specify. But it basically takes into account the redshift of the particles from the matter domination till our time. Okay, so you see that this formula is, it has the following more or less obvious dependence. It's proportional to the momentum, initial momentum of dark matter particle. So PT downstairs here is the thermal momentum of at that time. So it's just the temperature times some number. Okay, so you see that the smaller is the momentum of the particle, then the smaller if free streaming scale, and the smaller is free streaming mass. So if this guy goes to 0, then you will find that this mass is very small, and this means that the structures which have mass larger than that can be formed. The structure smaller than that cannot be formed, but larger than that could be formed. And when P is very, very small, then this goes under the name cold dark matter. So it's called cold because momentum P here would be very small. Okay. So this formula also shows you immediately that neutrinos cannot be dark matter. Why? Because for neutrinos, this factor would be of the order of 1. Neutrinos at the temperature of the order of electron volt are still relativistic particles, so this guy is of the order of 1. Here, for the mass, you will have to put a small number, electron volt or even fraction of electron volt. That will make this guy very, very large. And if the dark matter were neutrinos, then small structures, such as galaxies, would not be formed. But we observe them, so this dark matter candidate is out. And dark matter candidates such as ordinary neutrino is called hot dark matter. Okay, and it's called hot because this guy is of the order of 1. And then there is the whole spectrum of intermediate cases, which goes under the name warm dark matter, but the notion of warm dark matter is not very well specified because it's interpolated between these two regimes. Okay, so this picture it demonstrates the results of numerical simulation of structure formation, which just show what I just said. So if what this picture shows. The color code is that the brighter the point is, the more matter you see there. Okay, and then if you take hot dark matter, such as neutrinos, then this is the picture at large scales. And if you take cold dark matter, then this is the picture. And so here you see there are much more structures on small scales, and here the number of these structures is much smaller. And this is some intermediate case. And so here you will get a lot of small-scale structures if you talk about cold dark matter, and here you will get hot dark matter. Okay. And actual consideration, question. Yeah.
About the warm dark matter situation. In this case, it's 50% of warm and 50 of cold in this warm dark matter situation.
No, you don't consider that as 50-50%. It's just a different thing. It's just, no, this is not, if you would get a mixture of the two, you will get a different picture. No. When I say warm dark matter, you just say that all dark matter particles, they have some typical momentum, and that leads you to a particular free streaming scale. So if you have a mixture of cold dark matter and hot dark matter, then this is like a liquid with two substances. For cold dark matter part, this free streaming mass will be very small, and for hot dark matter component, it will be large. Okay.
I ask you this because usually in graduate cosmological books, because we must to do the perturbation theory using some kind of distribution function. So to freeze out of a cold dark matter, you consider that the energy is basically the mass. And to freeze out of a hot dark matter, the energy is equal to the momentum. I've never saw a expansion of the energy that use more than one term. So I asking that because I understood what you said. Is a expansion with more momentum terms?
No, this is not about expansion, really. No, this is not about expansion. If you have what is called cold dark matter, WIMP, okay, you can do your distribution, expand over momentum, but at the end of the day, the free streaming scale which you get for this case is very small. Okay, it's much smaller than the scale of the size of the dwarf galaxy. Okay, and this is a very robust result. Okay, and using this very robust, so if you say that you have cold dark matter, then this is a very strong prediction. It tells you what is the structure of the universe, how many different halos you have, what is their size, etc., etc. And this is all very well described by the dark matter profile, which is called the Navarro-Frank-White profile, which shows that there is a kind of singularity for small distances. Okay, and this can be checked. This can be checked experimentally. So if you have cold dark matter, then you predict a certain number of structures at very small scales. Okay. You predict these structures at so small scales that this dark matter objects, they do not attract baryons and so there are no stars in them. So these are really dark matter halos which contain dark matter and no stars. Okay, they contain no stars, so you cannot observe them watching the stars, though you can observe them potentially through gravitational lensing. Okay, and there is a very specific prediction from CDM paradigm how many lensing event you're going to have. So if you check that, and people expect they will be able to do so in next few years, then they can or reject CDM hypothesis just completely from this type of observations, or put constraints on different warm dark matter candidates. So this is actually a very exciting subject, I would say, because people are looking for WIMPs, weakly interacting particles, which is a cold dark matter candidate, okay, in different ways. There are direct searches, there are indirect searches and experiments, so there is a third way, okay? And you're doing astrophysics, and then you can, if you don't see that there are these small halos, you can just remove out WIMPs from from particle physics discussions. Okay, so the conclusion about this generic dark matter constraints is what do we know about dark matter particle? So we know that their lifetime is greater than the universe lifetime. We know that relatively weakly interacting dark matter particles should be very weakly interacting. That we also know that dark matter should be sufficiently cold, because this possibility of whole dark matter is excluded by observations. If we are talking about fermions, the fermions should be more heavy than 500 electron volts. And if we talk about bosons, we know that their mass should be greater than 10 to the minus 22 electron volts. So as a result, besides that, we know very little. Okay, and so we have a huge span of masses for dark matter candidates, which are all fine from the point of view of observational cosmology. So we have this huge span of masses, and one can try to narrow the search of different possibilities using different biases. Okay, I am not going to discuss in great detail different dark matter candidates. So now it's kind of a fashion. If you have a dark matter conference, the organizers ask people to vote. So what is your preferred dark matter candidate, okay? And this votes are time dependent, but I think that the current, how would I say, voting is as follows. So most of people vote for WIMP, weakly interacting massive particles, which is a cold dark matter candidate. Then second place is Axion, and during last years, the fraction of Axion votes went up, and fraction of WIMP vote went down. Okay, and then the third dark matter candidate is usually sterile neutrino. Fourth dark matter candidate is none of the above. We don't know what is that. Okay. So I'm not going to discuss here WIMP, because it's number one, and you will learn about that from other talks on this conference or maybe elsewhere. I'm not going to talk about Axion. precisely of the same reason. But I will discuss a dark matter candidate, which is sterile neutrino. Well, I have my prejudice for that. Okay. Well, actually, I prepared slides about axions and WIMP, but I have no time. Okay. So the motivation for sterile neutrino dark matter candidate, it comes from neutrino physics, as I basically discussed yesterday. We don't have right-handed neutrinos. If we add them, then we can understand baryon asymmetry of the universe, we can understand neutrino physics, and we can also understand dark matter. And let me show you how. So imagine that you have right-handed neutrino. We know the Lagrangian for this theory. This is a seesaw type 1 Lagrangian. And now we can see whether this particle can fit the constraints on dark matter which I just formulated. So the very first constraint was that this particle should live long enough, right? And but in fact, the particle is unstable. It can decay into 3 neutrinos. Okay, so here is the diagram. Here you have a Yukawa coupling between N and neutrino. This is the Higgs field. This is normally Z boson. Okay, and so the first requirement for the parameters of the theory is that the lifetime of this particle should be larger than the lifetime of the universe. Okay, and this can be expressed through Fermi coupling constant, the mass of this particle, and the mixing angle. And mixing angle is simply a ratio of Dirac mass to Majorana mass. There is yet another constraint, is that in addition to this diagram which I drawn, where right-handed neutrino decays into 3 neutrinos, there is a loop correction to this process, which goes like this. N goes to neutrino. This is the Higgs wave. And then you have a loop constructed from electron W. And then you can attach a photon to W, or you can attach a photon to electron, to any charged particle which you have inside this diagram. You can compute the rate of this process, and if you have a decays of that type, so this is a very interesting decay because the particle produces something which you can detect, okay? A photon you can detect, and what is interesting here is that this is a two-body decay, so that the energy of gamma quanta is fixed. It's just mass of the particle over 2. Well, in cosmology, it will be redshifted if decay occurs far away from you, okay? And so what you can do, you can search for the line which you cannot attribute to different atomic transitions. And if you find this type of line, you say, aha, I see something interesting. And in fact, the most stringent constraint, it comes from here and not from the lifetime. And this constraint looks like follows. So this is the mass of this dark matter candidate, and this is its lifetime. This is the universe lifetime times to the 8, and these are the constraints. Okay, so you see that the width against this decay must exceed by many orders of magnitude the universe lifetime. Have a question?
My question is, how do we expect to produce this N, like for experiments?
For experiment?
Yes, because how we try to detect this gamma, right?
Yeah, for experiment, you are ahead of me. I will come to that.
Okay, thank you.
First, before producing that in experiment, we should produce these guys in the early universe, right? how do we produce them in the early universe? It's the same process, inverted process in comparison with their decays. You can have neutrino anti-neutrino annihilation, then that boson, and then we have this neutrino. Okay, the computation of the rate of this process is somewhat involved because if you just naively estimate this diagram and use zero temperature Feynman rules, then you will get a result which is wrong by about 15 orders of magnitude. Okay, this happens because the medium is very important for that, and in fact, the way these particles are produced is to some extent very much familiar to MSW effect, which we have in the sun and which explains neutrino oscillations in the sun. So because of lack of time, I'm not going to discuss that in any details, but just tell you the result is that by doing this analysis, you find out that the temperature at which these particles are produced is roughly about 250 MeV. Okay, that leads to quite a number of uncertainties because 250 MeV is the temperature at which QCD phase transition or crossover happens, and so this is really a complicated phase of the universe expansion. Okay, but you can do this analysis, and this is if I go back to the terminology which I introduced, freeze in or freeze out. So this is freeze in. We start from a situation when there are no particles, and then they are driven towards thermal equilibrium. They never reach thermal equilibrium because they interact very weakly, but they are produced during this time.
You had in the previous slide a benchmark mass of 7 keV.
Yeah.
Why?
Yeah, I'll tell
why
you
in the
why.
keV?
Yeah, I just put 7 keV because of this little point at this diagram. Let me explain what this diagram is and what is this point. Okay, so this is the mass of the particle, and this is again the mixing angle, which I also discussed yesterday when I was discussing leptogenesis. Okay, so this is the mixing angle of this particle with ordinary neutrino. And again, the number 10 to the minus 10 means that the interaction of this particle with ordinary particles is 10 times 10 orders of magnitude weaker than the weak interactions. So this line here is constraints coming from non-observations of the line which would correspond to decay of this or that neutrino. Okay. This line is important because if the parameters would be here, then you would produce too many of them, and that will overclose the universe, and so this doesn't work. And then there is a specific point here which would correspond to 7 keV, which several years ago, couple of papers claimed that they do see a line which is consistent with decays of 7 keV sterile neutrino, and which is not consistent with explanation of this line by atomic transitions. Okay, so in a sense, this is a famous line. Whether it's true line or fake line remains to be seen, because okay, there were many groups observing that, but they were the same number of groups which were claiming that this is all fake. Okay, so this is a controversial subject, whether this line exists at all, and even if it exists, whether it indeed corresponds to something which cannot be described by atomic transitions. Okay, so it remains to be seen. What is important here, I said it remains to be seen whether this line is real or not, and that we should know within 1 year, I would say, maybe even less. Why we are going to know that is because of the following reason. So the whole controversy about this line, so if this is energy and this is intensity, so if you look at the data points which people present when they see this line, then by naked eye, you don't see it. Okay, so you have to do an analysis, you have to subtract the background, etc., etc. And the trouble in doing so is because the satellites which were used for analysis of this line, they have not very good spectral resolution. So this spectral resolution is about 100 electron volts. Okay, and if you have 100 electron volts, the line should be very, very narrow. You can get other lines within. And so the whole analysis gets tricky and not absolutely convincing. Let me put it in this way. But this year, there was a new satellite which was launched in September, which is called XRISM. Okay, so this satellite is actually a replacement of another Japanese satellite which was launched several years ago, and it didn't work well because it was just launched and then it was disintegrated because of human error, actually.
In the above plot, what is the region of parameter that provides the right abundance of dark matter? Can you show, please?
Sorry? Yeah.
In this plot, there are region of parameter that provides the right dark matter abundance.
Yes.
Where,
yeah. So
where is
you everywhere, well, everywhere here you can get right dark matter abundance
okay.
in cosmology, and then here this region is not good. Okay, so this region is excluded experimentally. Then there is the part which is, so for instance, here you see 0.5 keV. This is exactly Tremann gun bound. Then there are some strong bounds based on analysis of structure formation and Lyman alpha forest. But basically, this region here, it's okay from all points of view. Okay. And this is the line. And these lines here are shown to see sensitivity of future experiments which do not exist yet. Well, anyway, this new instrument, which is called CRISM, it has a energy resolution which is 10 times better than all the previous instruments, and this instrument will not be able to cover all parameter space, but it will for sure exclude or confirm this line. So whether this is fake or not, 7 keV neutrino, we should know relatively soon. Okay, so that's all what I wanted to say about, yeah, there was a question, how do we do that in the laboratory? Yeah, that's a very, very good question, because suppose that in future, XRISM or maybe some other experiment will find out some line which comes from dark matter. Okay. Can we be sure that this is indeed sterile neutrino dark matter? The answer is no. Why not? Because imagine that you have another dark matter candidate, a scalar particle, and this scalar particle decays into gamma gamma. And this scalar particle has a mass 7 keV, for instance. Okay. There is no way, by analyzing this line, to see whether this gamma quanta came from decay of fermionic particle or scalar particle. Okay. So in this case, we will learn that, okay, we have light dark matter, which decays into 2 photons, or say photon and neutrino, but strictly speaking, we don't know what it is. Okay. Then we should be able, then it would be our wish to create this particle in the laboratory and find out whether it indeed exists. Okay, and there is one experiment, well, at least one, where people are trying to answer this question. And the idea here is basically the inverse beta decay. So if you have some nuclei, okay, so this nuclei, there is inverse beta decay, meaning that you have a process n plus electron, say from K shell, goes to n prime plus neutrino. Okay, but since it can be neutrino, there could be also a process. So this is nuclear. This is not our right-handed neutrino. So there is a process like that, nucleon plus neutrino, and then there should be a process like our sterile neutrino. Okay, and then by study kinematics of this process, you can distinguish this from this, and so you can potentially find out this particle. But these are extremely challenging experiments. Other things would be, say, tritium decay. So if you have a decay, how the neutrino mass is searched for, you look at the end spectrum of electrons which occur inside tritium decay. Okay, so here you would get some little kink at the electron spectrum, which would correspond to this particle, which is somewhat heavier. But with these parameters, which I just described, it won't work. So the interaction of this neutrino, this mixing angle, which I just shown to you, it's too small for this particle to be discovered in ordinary beta decay. So that looks to be the most promising possibility. So if there are any more questions about this particular dark matter candidate, I can answer. Otherwise, I will turn to inflation. Okay. So let's discuss inflation, and I will go. I'm going to discuss the following points. We will discuss the problem of initial conditions in the expanding universe. We'll discuss horizon problem, why universe is homogeneous and isotropic. Up to now, we were taking that as for granted, as God-given. Then we will discuss flatness problem. So remember, in our determination of cosmological parameters, omega matter plus omega lambda was equal to 1 with high accuracy, and it would be great to understand that. And then I will tell you about idea of inflation, and I will tell you how this idea can be realized with the simplest possible theory, free scalar field. Okay. Okay, so horizon problem. If we forget about universe expansion, then if you have two events separated by some interval, so s is equal to t squared minus x squared. So if s is negative, then you know that the event number 1 and event number 2 are not causally connected. Okay? Why? Because simply the speed of light is finite, and in this case, there is no information exchange between these 2 points. Okay? Let's see how this is changing for expanding universe. So what we have to take into account that the space-time is not static, and so that the light, though it propagates with the speed of light, then there is still a Hubble flaw, which makes different points to lie from each other at larger and larger distances. So how do we do that? I write the same equation which I wrote to you when we discussed free streaming scale. The only difference is that I put here 1 because the light propagates with the speed of light, which is equal to 1. So we find this distance which the light propagates in expanding universe. Now we can plug in the scale factor, which corresponds to for instance, radiation-dominated universe or matter-dominated universe. So these factors are temperature to some power, which is less than 1. What you observe, and that's a very important point, that if you insert these behaviors, this one or this one, in this formula, then you can safely put initial time to 0 because integral converges. Okay, so meaning that there is, from this point of view, in this quantity, the scale of horizon, there is no singularity if you have radiation-dominated universe or matter-dominated universe. And so what you find that for radiation-dominated, you get 2 times t. For matter-dominated, you have 3 times t. If the universe were not expanding, you will get just t to the first with coefficient equal to 1. Okay, so conclusion from here. So if the universe was dominated by matter or by radiation, then if you have points and distances larger than that, and this number is called horizon, okay, so you don't see behind horizon, that's why it's called horizon, then these points were never in causal contact with each other. And therefore, if you look at this picture for our universe, we should expect that if we have the 2 points, the distance larger than horizon, then these 2 regions of space should have different temperature, different density, different everything, because they simply never talk to each other. So let's confront now this knowledge with what we know about cosmic microwave background radiation. Okay? As we discussed, cosmic microwave background radiation is decoupled at temperature at Z 1100, so that was well in the past. Okay? And what we see now, when we observe cosmic microwave background, we see a snapshot of this radiation. And so this is the picture which shows what we have. This is the distance scale, this is time, this is the present time, and this is the time which corresponds to recombination. Okay, and so let's now find the size of causally connected region at the time of recombination. And then we would expect that, well, here in this domain, the temperature has 1 value. In this domain, the temperature has another value, et cetera, et cetera. Or the same picture is here. So we are here in the center of the universe. Yeah, this is the sky. These are different directions in the sky. And then we can look in this direction, get cosmic microwave background, in that direction, get a cosmic microwave background. And then we can also estimate the angular, the angle where you get this domain, which is causally connected. Okay. How do we estimate that? Okay, very simply. First, we take the this factor, and this is time of decoupling divided by the time which we have now. And this shows us the angle of the domain, which is causally connected. But this has to be corrected by the fact that the size of this domain increases because of universe expansion. Okay? And this is nothing but expansion in matter-dominated era. So we have here this ratio to the power 2/3. And as a result, the angle theta in which you have causally connected patch of the universe is of the order of 2 degrees. Okay, so what this computation shows, that if we apply this causality arguments, then the temperature should vary a lot, of the order of 1, if we change the light of sign by 2 degrees. Okay, but this is not what we observe, right? So what we observe that everything is isotropic with accuracy 10 to the minus 5. So meaning that we made an error by 5 orders of magnitude. And this problem is called a horizon problem. There is yet another problem which is actually closely related to that, which is called flatness problem. And to understand flatness problem, we do the following. So if we have a sum of abundance of matter, of cosmological constant, and of radiation, we can rewrite our Friedmann equation or Einstein equation, whatever you prefer, in this form. So that all this sum of all these abundances minus 1 is equal to the coefficient which tells you whether our universe is flat, open, or closed. And then this is divided by the scale of the universe and the Hubble constant. Okay, so if you now take again radiation or matter-dominated universe, where R is a power law to some power, and the Hubble scale is always some number 1 over t, because I remind you that the Hubble scale H is simply R dot over R. Okay, so you insert this dependencies here, and you find that the right-hand side, omega minus 1, increases with time. Okay, and now you say, okay, now we know that this difference is very small, well, 1% experimentally. And then in order to have that, then this means that in the past, omega should be much, much closer to 1 than we have it today. Okay, and then the question appears, okay, how the universe at the very beginning knew that it should produce for us the universe which is almost flat. Why the universe was so flat at the very beginning? So if you take, for instance, the time corresponding to Big Bang nucleosynthesis, then this difference, omega minus 1, should be of the order of 10 to the minus 15 if you want to fit the present number. And then this number should be even smaller if we go back in time, if we consider the time of baryogenesis or something else. Okay, so the these experimental facts, they tell us that the present universe is flat, homogeneous, and isotropic, but this is very bizarre, because we would expect it to have a lot of fluctuations and the angular scale of the order of 1-2 degrees, okay? And the question arises, is there any rational way to understand that? Okay, and maybe trying to understand that, we can learn something new, make further predictions. Okay, and the possible answer to this question is yes, and it is associated with inflationary theory. So what is the main point of inflationary theory? So in the consideration which we just carried out, I said if. I said if the universe was matter-dominated, if the universe was radiation-dominated at the very beginning, we have all these problems. But the mere assumption that the universe was dominated by matter or by radiation, it doesn't follow from anywhere. Okay, so we do know that now the universe is dominated by cosmological constant or by dark energy. Sometime in the past, the universe was dominated by matter, for sure. Even before, at the time of BBN, the universe was dominated by radiation. Okay, and we have a lot of we have experimental data which confirm that. But the extrapolation of that to even earlier time is not substantiated by any data. And therefore, it may be wrong. And we can easily modify, theoretically, now for the time being, the law of expansion of the universe, in which none of these problems, the horizon problem or the flatness problem, will ever show up. And so the idea is the following. So this was our initial picture. Okay, so this is space, this is time, and here I plot straight curves corresponding to matter-dominated expansion or radiation-dominated expansion. And now I'm going to do the following trick. Okay, I say that the recombination is here, but well before recombination, well before nuclear synthesis, our universe was expanding much, much faster than for radiation-dominated or matter-dominated case. Okay, let's ignore for a moment why it expands faster. Let's just assume that this is the case. And then you can make this assumption. This assumption is certainly safe if we are talking about the time, say, before baryogenesis at temperatures more than 200 GeV, for instance. Then the universe expands fast. Then the causality patch is very small. Oh, sorry, is very, very large, much, much larger than causality patches which we saw before. And now, if we look at the past, what we see, we don't see this many patches which would exist for radiation or matter-dominated universe, but we just see one and the same patch. Okay, and since it's one and the same patch, then that's it. We understand why the universe is homogeneous and isotropic. Okay, so and now a way how this picture can be implemented. So let's say that from beginning, well, time equal to 0, from singularities up to some point, we had expansion universe with some equations of state which we don't know, and so we don't know what was happening. Then suppose that from this time t0 to some other time t1, the cosmological constant was dominating. And then, when cosmological constant was dominating, we already know that the universe expands exponentially. Okay, so it expands very fast, and so we have an opportunity to make a huge causality patch. Then we should come back to what we know, to radiation-dominated universe, and that means that at some time t1, this cosmological constant domination is transformed into radiation-dominated universe. So Big Bang happened, okay? And after that, we have a standard Big Bang cosmology. First with domination of radiation, then with domination of matter, and then with domination of dark energy. So once we accept this hypothesis, then this is how the scale factor of the universe will be behaving. And this time, between T0 and T1, I said that the cosmological constant dominates, and so we have exponential expansion. Okay, and our scale factor was going up very fast. And then at time equal to 1, this exponential expansion is converted into the power law, which we have in the radiation-dominated universe. But R is a continuous function. Okay, so here you see that we have power law, but this guy should be equal to this guy when time is equal to T1. Okay. Now we can compute the horizon at recombination of microwave background, and this horizon will be this exponential function, and this is again the h is the Hubble rate at during the exponential expansion. Okay, and so if we require that this horizon at recombination, that this number is larger than what we see, then that's it. We solve all the problems. So numerical example, let's say that maybe Grand unified theories are right, and maybe Grand unified scale, which is of the order of 10 to the 15 GeV, is determining the exponential expansion of this very early universe. Then, to have this guy big enough to solve all our problems, it's sufficient to have inflation, which has 65 e-foldings. So the number e-folding means that this product, h over t, is 65. And so even if the initial horizon was extremely small, it was extremely microscopical, then after this expansion, it gets very, very large. Okay. So that solves the causality problem, and that solves the flatness problem simultaneously, the same footing. So if you had initially the universe, which was very bumpy at small scales, then the inflation inflates all the scales so much that all these bumps disappear, and within one patch you have something which is extremely homogeneous. Yes? Sorry?
This that you just told us is why baryogenesis cannot be taken as an initial condition.
I'm not sure I got the question.
This, you said that the initial fluctuations will be diluted. Is the same explanation why baryogenesis is not an initial condition?
Yes. Yeah, this is certainly related. So exactly. So there is a relationship to baryogenesis. If you imagine that there was an initial condition which had some baryon asymmetry, then this baryon asymmetry will be diluted as exponential minus h times t.
The e-folding.
And then it's all gone.
Yes.
Yes. Okay, so this is the picture, and now we can ask ourselves whether we can suggest a field theory, or quantum field theory, in which this happens. Okay, and very surprisingly, you can get inflation, you can get all these explanations already in the theory of non-interacting free scalar field. So what's the idea behind? So this is chaotic inflation by Andre Linde. So this is the potential of our theory, and this is our phi square dependence. Okay. So normally we would say, well, if we have a picture like that, then our system should be in a ground state, so phi field should be equal to 0. But there is no much rationale behind that. We can say that the initial condition of our system, we are talking about very early times where quantum gravity perhaps plays a very important role. And so that it's quite conceivable to assume that initially the scalar field was not at phi equal to 0, but somewhere else. And moreover, we can say that the universe was very complicated. There were large fluctuations. The scale, the size of this fluctuation maybe presumably was 1 over m Planck square, because this is a quantum gravity. And then in different patches of the universe, lived their own life, okay, with large values of phi, and some of them phi is large, and others some was small, etc., etc. We don't understand what it is, so we can say that this is space-time form hiding our ignorance behind some nice words. Okay, then we can ask ourselves what is going to happen with the scalar field in different patches. So this is, of course, a complicated question because quantum gravity perhaps is important. But let's look at this space-time form and find a specific patch in this form in which the energy density is dominated by the potential term. Well, not necessarily very much, but somehow dominated, so that potential is greater than the gradient, and the potential is greater than, so to say, velocity of the scalar field. Okay, so we take this patch. In this patch, we can approximate our scalar field as being constant, doesn't depend on space, and then we can consider the dynamics of this scalar field, simply writing the action for this field and coupling this field to gravity. So you can do that, and from there you can find equations of motion for the scalar field. So this part of equation of motion, you of course know very well that will be equations of motion in flat spacetime. And the fact that the universe expands with some Hubble rate, it adds one more term which looks like this. Okay. So this is all coming. You can exercise for you. Take the action, which is equal to m Planck square over 2 r. This is the gravity part. D for x square root of minus g. And then add the action of the scalar field, d phi square 1 over 2 minus 1/2 m square phi square. Find the variation of this action with respect to scalar field. Okay, and that's what you are going to find. This parameter h, which is the Hubble rate, it's related to the energy of the scalar field, right? So this is one of the Friedmann equations. So you get a description which is, well, nonlinear with respect to the scalar field because this friction depends on the parameters of your theory. Qualitatively, you can understand very easily what is happening. The Higgs field is misplaced here. When the Higgs field is large, you see that the Hubble rate is proportional to potential, and potential is large. And this means that the friction is large. And if you have harmonic oscillation, oscillator with large friction, then the system drifts slowly in this direction. It doesn't oscillate, it's just moving slowly. And this slow motion is named slow roll inflation. Okay? And slow roll inflation means that the Hubble rate is much greater than phi double dot divided by phi dot square. So in this domain, the motion of the scalar field is very easy to analyze. How do you do this analysis? So you suppressed this term, because this is a slow roll approximation. You can neglect phi dot. H is a function of, there is a misprint here. So this is H square. H is a function of the scalar field. Okay, so you take this equation, you forget about this term, because this is slow roll. Acceleration is not important, just these two guys. What I did, I replace H here by this value, and this is the first term, and then this is the last term, m square phi, which is derivative of the potential. Okay, and then this equation is elementary. You can solve it very easily, find phi cancels, and so you find that the solution is that phi is decreasing, phi is drifted in this direction, and this is the way how this phi field is decreasing. Okay, so after some time, our assumption about slow roll becomes invalid. This happens when our phi field reaches the point of the order of m Planck, and after that, we will get the damped oscillations. Yes?
Thank you. It was not clear to me why we needed the slow roll condition in the first place. Why do we want the field to slow roll on the potential?
Okay, we will see that a posteriori. Let's take it like that. Let's suppose that this is true, and then we will see what will give it to us. And we will see that what it gives to us is very satisfying, and that's why we take this condition.
Thank you.
Okay, so we will see, well, eventually that in this case, we will get inflating universe with sufficiently large number of e-foldings. And if this is not true, this is not going to work. Okay, so that's the short answer. When the time goes, as I said, we are reaching some point where our slow roll condition is not satisfied, and after that the universe is oscillating. Okay, so let's see what happens during the slow roll. So our phi field, though it's changing in time, it's changing in time very slowly, and there is a large energy which is of the order of m square phi 0 square, which is potential energy which is sitting in our scalar field. And once we have large energy sitting in the scalar field, this means that our age is approximately constant, and this means that our universe expands exponentially. Okay? And we can estimate what is this factor, ht, here, and this gives us the number of foldings. And putting all the numbers in place, we see that the number of foldings is a ratio of two quantities. One is the Planck scale, and another is the mass of this particle. Okay? And so if you say that this ratio is greater than 65, then that's it. The job is done, the universe is homogeneous and isotropic, and we live in the patch of the universe which satisfy this property. And so coming back to your question, we can take the initial state of our field, which is not at large values of phi, but which is at small values of phi. Okay? Then the slow roll condition is not satisfied, but in this case, the universe does not expand exponentially. Okay? So if we started from this space-time form where different initial conditions were used, then there are patches in which initial value of the scalar field is too small, okay? And these patches do not expand exponentially. We don't live in them, okay? But there are other patches in which the universe were expanding exponentially, and we can say, aha, these are exactly the patches which we happen to live in. Okay. Okay, so this is yet another picture which shows more or less the same thing. This is the scalar field. This is the energy. Then there are very, very large values of the scalar field about which we cannot say much because they're so high that quantum gravity should be there. Then we are entering in the regime which I just discussed, the regime of slow roll, and then there are fluctuations here. Okay? And you see that here you kind of kill with one stone many, many things simultaneously. So when the scalar field oscillates at the latest stage, so it oscillates and then it transfers its energy into everything else, say in the particle of the standard model. And when it does so, the entropy is generated, and we can say that Big Bang happened. So after this energy is transferred, we get a hot universe. So why do we get, again, the hot universe? Because the system wants to be in a state with the largest possible entropy, and so everything, all the processes will be driving universe in this direction. There is yet another point which is also very important, which is associated with this process of slow roll. So the discussion which we had up to now, it was completely classical. Okay, so I was saying that we have classical equations of motion, we solve them, etc., etc. But this is, of course, an approximation. And in reality, everything is quantum. And as you know, if you have whatever quantum theory or quantum mechanics, then there are quantum fluctuations. Normally, if we are talking about large distances, these quantum fluctuations are not important. Well, or they are concentrated on many, many very, very small scales, like atomic scales, etc. But here we have inflation. So something which was happening at very, very small scales gets stretched and get transformed into larger scale because of the exponential expansion of the universe. Okay, so what you can do, you can pose the following problem. You can say, okay, we take here into account quantum fluctuations. They should be there. And then we consider what happens with this fluctuation in this exponentially expanding universe. And what you find that there are density perturbations at large distances. Okay, and that's a great thing, because if you have an absolutely homogeneous and isotropic universe, you won't get a structure formation in this theory, because to get some collapse of different objects leading to galaxies, etc., you need some initial, maybe small fluctuation. And now the quantum fluctuations are leading to that. Okay, so this comes, so to say, for free. Okay, so this is shown on this picture. You have that at quantum small scales, and then you get that at macroscopic scale. You can, once you have, I was talking about free theory. Okay.
Just to make it more clear to me, in this idea of chaotic inflation, you have this spin space-time for once, and things happens more or less like the bubble nucleation. Some of them gets inflated and
yes,
nucleate with all their space-time photons, and the whole universe inflates. That's the idea. I got it right.
Well, you can say that it looks like bubble nucleation. I'm not sure that that would be a good analogy. I mean, I'm not sure that you can use this analogy for getting out anything out of it. Yeah, I would better think that you have this inhomogeneities, because you see, if you talk about well, bubble nucleation, etc., which occur at finite temperature, so there the gravity effects are not as essential as here, because what is essential here is that you have a patch with overdensity, then it starts to expand exponentially. Another patch doesn't do so. In finite temperature phase transition, you don't have that. Unless you have some
And
huge,
also
huge
a bubble expands in space.
Yeah.
But here is space that expands.
Yeah, that's also a good point. Thank you, Enrico. Okay. Now, once you have this picture, you can make this picture detailed and elaborated. Okay, I said to you, okay, we take the scalar field, which is free scalar field. This is, of course, an oversimplification. If we have a scalar field, then it perhaps has some interaction, it has some non-trivial potential, etc., etc. But you can elaborate this picture theoretically very, very far. So you take whatever scalar theory you have, maybe with few scalars, then again you can use this idea to see how the universe evolves, how density perturbations appear, etc., etc. Okay, so this you can develop very much. And let me just, so how much time do I have? Okay, so I will tell you a few more things, and then I will stop. So one of the quantities which you want to compute in this picture is the correlation function for density perturbations. Because this thing you can measure observing cosmic microwave background. You can observe that eventually by using baryon acoustic oscillations, and you can observe that by analyzing the universe structure. Okay, so one of the predictions of inflationary theory is this type of correlation function. Here you have average density, and this is density at point x, density at point 0, and this is some function. Okay. The simplest form of this function is power law. So you say that this guy is the distance between these 2 points to some power. Okay, and this exponential here, ns, is called spectral index. Again, this is a spectral index of scalar fluctuations. If the spectral index, ns, is equal to 1, then you get a scale invariant spectrum. So this spectrum kind of doesn't depend on x. And this spectrum, it has a name. It's Harrison-Zeldovich spectrum. Okay, and just from our ideas that the universe is expanding and we are in the same causality patch, without computation, we can conclude that ns should be indeed some number close to 1. Why so? Because if we are in one causality patch, then everything was stretched, okay, and should not depend on the distances. So this should be constant, and we have this constant only if ns is equal to 1. So this is an oversimplification, and whenever theory you take, phi-square theory, which we consider it, or more complicated theory, you can do a computation and find out this parameter ns. Okay? And this is an important parameter which people find, say, in analysis of cosmic microwave background radiation. There is yet another parameter of inflation, which is a ratio, a fraction of energy sitting in gravitational waves to energy sitting in scalar perturbations, and which is normally called R. Okay, so you had in Mikhail lectures the analysis of gravitational wave production at, say, phase transition. So here, similar analysis can be done, and it can tell you what is the fraction of energy sitting in gravitational waves. Okay. And once you know these 2 numbers, ns and r, you can confront your knowledge with observations, and these observations are observations of cosmic microwave background. So in analyzing cosmic microwave background, you can look at the temperature in different directions, okay? And using that, you can make a theoretical prediction for this function. This is not straightforward, because you have an initial spectrum of fluctuations, which is later modified by different processes, such as, because you have a plasma, and the electrons, photons exist in this plasma, they interact with each other, and so this guy is not a simple repetition of this scale invariant spectrum. It gets modified when different standard model processes are taken into account. Okay? And how this analysis is done? So you have this picture of inhomogeneities of cosmic microwave background radiation, which contains hotter spots and colder spots. You take this picture, you analyze this picture statistically, and you get this. Okay, and this is the result. This is the angular scale, and this is temperature fluctuation. So you see here a peak at 1 degree. This is not a random thing. So remember, we found that 2 degrees is a causally connected domain. So you should expect to have something here. Okay, so you have the first peak. And then you have many other oscillations here. And these red points are experimental data, and this green curve is the theory taken at a particular value of cosmological parameters, such as NS, omega, omega baryon, omega dark matter, etc., etc. And so since you have many, many experimental points, and the number of parameters which describe the universe is much smaller, then you can check the consistency of your theory, and up to now no serious inconsistencies were found, and you can also fix different cosmological parameters which are well, fixed by this analysis. Okay, so I will think I will almost stop here, just saying you a few words. So we took a massive free field to get inflation. And that was initially when people started to discuss inflation, they said, aha, we discovered a new particle. This new particle is inflaton, and the mass of this inflaton is 10 to the 10 GeV. Okay, and so we see it on the sky. So this is a little bit brave, okay, because it happens that there are many, many theories which can fit experimental data here. At the end of the day, there are not that many inflationary predictions. There are just two numbers. There is the number which is the tilt NS, which I just discussed. Yet another number is R, and that's basically it. Okay, so once you have two numbers of explain, you can invent many theories which can do so, and this picture shows you that. So these are the typical pictures for inflationary prediction. So what is here is the tilt of scalar fluctuations, and this is tensor to scalar ratio, this parameter R. There are different points here which correspond different lines, which correspond to different theories, and this is experimental data, which tells that the spectral tilt NS is really close to 1, but different from it, 0.04 difference. The gravitational waves which are associated with inflation, they were not discovered yet. There are only upper limits, and there are many theories which can fit the data. Okay, so one of them is a hypothesis that it was a Higgs boson of the standard model who inflated the universe. And I think I'm gonna stop here and just make conclusions about inflation and general conclusions about the lectures I was giving here. So the problem of initial conditions of the universe, horizon flatness, can be solved by inflation. Inflation and Big Bang can be realized in dynamics of scalar field. There is a generic inflationary prediction that omega should be 1. So that's 1 because the universe was inflated, and that's exactly the explanation of the flatness problem. The byproduct of that is that quantum fluctuation of scalar field leads to density fluctuations in the universe. Analysis of CMB spectrum can fix all parameters. Well, the parameters which are used to describe our universe, such as omega, omega lambda, omega matter, etc., and also inflationary parameters. And where the particle which drive inflation is an open question. We don't know that. And Higgs boson is a possibility. And generic conclusion is that as you see, there is a very non-trivial interplay between particle physics and cosmology, which we see in many, many different areas. And during last, say, 40, 30 years, this interplay was strengthening and strengthening, and it was mutually benefiting for both fields, for cosmology and for particle physics. And I think we may be optimistic and expect new discoveries in the future.
Thanks, Mikko, for the last and exciting lecture. So, do you have any questions? I'm sure you do.
I didn't understand the maximum entropy argument you gave after inflation. Could you explain
Well, okay,
in a bit
yeah,
more
yeah,
detail?
I think, yes. Yes, so I was saying that there is some field, it may be some abstract inflaton or Higgs boson or whatever, which had initially slow roll, okay, and then it started to evolve much faster, okay, so it started to oscillate. This process can be analyzed theoretically. So if you know what the coupling of this field is to the particles of the standard model, you can start with these initial conditions and then see what happens when this field oscillates. Okay? So generically, when you have some time-dependent phenomena, like oscillating fields, they lead to particle production. And you do see that indeed the particle production occurs. These rapid oscillations of the scalar field lead to production of fermions of the standard model and other particles. And then you can follow this evolution and you see that everything is thermalized. So this is so this process is called preheating or reheating, but this is the process which can be analyzed theoretically, and the result is that this coherent energy, so to say, sitting in oscillation is spread out over all the particles, and then they are driven to thermal equilibrium due to collisions.
I see. So the point is that during those preheating periods, after it ends, the universe follows the usual Big Bang evolution already in a thermal state.
Yeah,
I see.
That's correct. So it's it's indeed like this. So if this is some field phi, this is V, this is some potential. Up to here we have slow roll, and here we have oscillations. So you analyze that, and then you see that soon after that, everything is thermalized.
I see.
When this happens, again, it's an open question, which is model dependent. So for instance, if you say it was Higgs boson who inflated the universe, then the temperature at which the universe was heated up is roughly, 10 to the 13, 10 to the 12 GeV. If you take some other theory, this temperature can be higher or can be smaller. But this is a very rapid process. I said that there are oscillations here, but in reality, when you do numerical simulation of this process, then you see that kind of one oscillation is enough, and then everything is gone. All energy goes into particles.
I see. Thank you.
Thank you for your presentation. I have heard an argument from Joseph Silk that goes like this. He says, to access to inflation imprints and to discriminate about different theories of inflation, we must perform massive surveys on the hydrogen clouds from the dark ages. And to do so, we must build a massive telescope on the dark side of the moon. So what are your thoughts on this situation?
I'm not sure I can comment, okay. Okay, no, I mean, indeed, the moon, if it can be explored in different ways, that could lead to enormous progress. Okay, people discuss well, this telescope. Then there were a discussion whether maybe you can do a proton decay experiment at the moon, etc., etc. Well, maybe this is going to happen. I'm not so sure it will happen soon. No, I cannot really. At the moment, this is like science fiction, I would say.
Other questions? One more.
Just because you mentioned in the last few slides, so I got a bit curious. Could you briefly comment about the scenario where the Higgs is driving inflation? Because we, in this simple slow roll, we use that the mass scale of the inflation was close to relatively close to the Planck scale to get the number of E-folds we needed. So how does this happen with a much lighter Higgs case?
Yeah, here it happens in the following way. It depends on the way how scalar fields interact with the gravity. Okay, so when I was taking this scalar field example, I wrote some action here, right? So this action still survived. This action is not complete in the following sense. Other terms which are admitted in this action are some parameter xi times scalar field square times r. So if you have just this type of action, then this is called that you have fields which have minimal coupling to gravity. The word minimal means that you write your flat space action, and then you simply change normal derivatives to covariant derivatives in gravitational field. Okay, but that's not the whole story. Other couplings of different fields to gravity are possible, and in particular, this type of coupling is possible. Now, if you have this type of coupling, then the analysis of this theory is changing. If we have the standard model, then we also have a term lambda over 4 phi to the 4th power, right? So that would be Lagrangian of the standard model. So if you take now this theory, which is actually used in Higgs inflation, then you observe the following phenomenon. If you have large scalar fields, and we were playing with large scalar fields when we were discussing inflation, then you see what happens. So this guy you can neglect in comparison with this because phi is large and mass of the Higgs is small. But if phi field is large, you can even neglect this guy. So you have dynamical Planck constant or dynamical Planck mass, which appears because of the interaction of scalar field to R. And if you have a theory like that, then this theory doesn't contain any dimensional full parameters. So this is a scale invariant theory. And if you have a theory which is scale invariant, this basically means that nothing depends on the scalar field. Okay, so you increase the scalar field, you say, I increase the mass of the top quark, but you're not going to notice that because you increase the constant of gravity, and in physical units, nothing changed. So what does it mean? This means that if you now plot the potential of this theory in physical units are associated with so-called Einstein frame. I can explain what it is, but okay, it doesn't matter. So this physical potential, it will be like this. And then this plateau is a perfect playground for inflation because everything can be inflated. And so in spite of the fact that the Higgs is very small, the existence of this plateau leads to inflation.
Thank you.
I think maybe we can go for the coffee break and then can try to be back at 5. Okay, thanks. Okay.